Hello everyone, and thank you for listening in to this presentation. My name is Anne Ton, and I'll be telling you about my PhD research, which I do together with Vincent Fuik and Stefan Arninkhoff at the TU in Delft. Today I'll be telling you about morphodynamics of sandy beaches in low energy non-tidal environments, of which you see an example here in this picture. These beaches in these locations are often overlooked a bit because most research is about high energy tidal environments, for instance on open coasts of oceans and seas. But these are also very interesting, and we don't fully grasp the morphodynamics in these locations very well just yet. And they're not only interesting from a scientific point of view, but also a practical point of view, because there's a few locations in the Netherlands where these have very important function. So it's important to understand what's happening there. So let me zoom out a bit to show you what I mean. Over here in the Netherlands, we have two big lakes, the IJsselmeer over here and the Markermeer over here. And the picture that I just showed you is of these islands in the middle of the Markermeer, called the Markerwadden. On these islands we have these sandy beaches and also dunes protecting the nature area behind it, which is constructed there for improving water quality and for wildlife. So they have an important function of protecting that. And there's another project going on the dam between those two lakes called the Hydrodijk, where these sandy beaches are used as protection of the dike. And here you can see the pilot study done for that purpose. So here they even have the function of flood protection for a big number of people. So they are quite important. And what's also very nice about these locations is that we can use them as study sites to understand these morphodynamics a bit better. So let's first have a look at the morphology at those locations. Well, here we have the profiles of the cross-section of pilot Hydrodijk. The water level in this lake is over here around minus 0.3 meters NAP, and NAP is the local Dutch datum. They have a very steep beach face around the waterline, of course, and that connects them to a platform which is almost horizontal, which connects again to a slope going down here to the original Markermeer bottom. And the lake is very shallow, as you can see. That's why we also have these low energy waves, because they're depth limited. Then when we look at those other locations, we have three measurement sites at the Markerwadden. We have Noorderstrand, which is on the northern side of the island, Recreatiestrand over here near the harbor, and then Zuiderstrand on the south of the island. And these other three locations show a very similar shape. Also the steep beach face, a platform, and the offshore slope. Only here it's a bit deeper because it's in the middle of the lake. And what is interesting is that all these profiles, they don't only share the shape, but they also share the elevation of the platform, because at all locations it's about minus 1 meters NAP. And we were very interested to see why that is the same in all those locations and what is the relation to hydrodynamics, because it deepens to this elevation quite quickly and then stays around that point. So we were thinking whether it had to do with the depth of closure. And here you see the formula calculating this depth of closure, the original definition by Hallermeyer. We went back to this original definition because he validated this formula with laboratory tests in flumes where they had constant waves on an initial plain sandy slope. And he schematized the results of all these flume tests in this figure. You can here see the initial plane slope and then the final profile after the flume test is done, which looks of course very similar to the profiles that we see in the marker mirror. And then he validates his formula with the depth of this platform, which is, of course, also interesting. And so it should give a good proxy for the depth where wave-induced sediment transport is negligible, which is different from how it's used often nowadays, where it's used as a limit, ultimate limit of where morphological change is not happening anymore. So we're really looking at a proxy for this depth of closure by this original definition. Well, then the input for this formula is just a wave height and wave period, but not just wave height, of course, the one during the storms. And then he uses the 12-hour exceeded wave height, which is illustrated very nicely in this figure by Nichols. You can see here the wave height over time during a storm. And then the 12-hour exceeded wave height is quite literally the wave height that's exceeded for these 12-hour periods. And we calculate the depth of closure, we want to calculate it for every storm. So we do this for all the peaks. And here is the signal of our wave height near the pilot hoogte, because we have a very long sequence of that. And this is a stormy period in November 2015. You can see the wave height in blue over time. Then we selected the peaks with the orange pluses. Then we calculated for every moment the 12-hour exceeded wave height, and then found with the red crosses the values corresponding to each storm peak. But because the water level is varying quite a lot in this lake due to a wind setup, we use the same method to find the wave height of the water level for every storm, using the same method at those storm moments, which is then also the 12-hour exceeded water level. Well, then we plotted them in this figure. So in blue you see those peak wave heights, which are a bit higher. Still not very high, of course, but they exceed 1.20 meters at some points. And then in orange you see the 12-hour exceeded wave height that we used to predict the depth of closure with the Haller-Meyer's formula. Here in orange you see the 12-hour exceeded water levels that we used, and then we subtracted the depth of closure from that, and then we get to this green line, which is the predicted depth of closure. Well, we combine that to the black line, which is the actual platform elevation. You see it starts a bit higher up here because that's just after construction of the profile, and a platform is not present at that point. Then it relatively quickly goes down and stays around at -1 meters NAP. And it coincides very well with this predicted depth of closure. So that would mean that the elevation of the platform is actually at that elevation where wave-induced sediment transport is negligible. Well, we combine this information with some other analysis, which I cannot show you due to time. For instance, the one of sediment budget, to present to you a conceptual model of what actually happens over time. So we start off with a calm period. Then we usually have erosion of the beach face, which coincides with a growth on the platform or accretion. That's why we think it's mostly cross-shore. Then this sediment on the platform can move around both in cross-shore and long-shore direction. And then a stormy period enters, where there's also erosion of the beach face over a bigger area because of higher waves, of course. And then if we look at the depth of closure during the stormy period, that will be deeper because of the accretion in the calmer period over here. And that's why there is then erosion also of this area, which can go in both directions. And this sediment is then transported also over the edge of the platform, we think, where it's transported down due to mostly gravitation. And then the platform builds out in this direction. And we think there might also be some longshore transport over here due to wind-driven currents. And that is our conceptual model. So we do not say that there's no transport over the platform, but because of the calm and the storm periods alternating, there is a balance, and then the platform finds itself at around this depth of closure. So to conclude, these low energy beaches typically have these narrow beach face and low gradient platform. That's not only the case in these Markermeer beaches, but also on other locations we found in literature. The development of the platform is both due to cross-shore and longshore transport, and the elevation of the platform is approximately at the height where we find a depth of closure, so wave-induced sediment transport should be negligible. And then the horizontal development, by which I mean the erosion of the beach face and the build-out of the submerged slope, has not reached an equilibrium yet. We followed this pilot study for 4 years, and there was still changes going on. So we're curious to see whether an equilibrium is possible and under what circumstances, but that's for further research. That concludes my presentation. I hope to be able to answer some questions live after this, and hopefully I'll also publish a paper about this soon, so you can read more about it. Thank you very much.